to start my course. So it will be on birational invariants from Gromov-Witten theory. Yeah, so this is the title, and in fact there is much more. So this birational invariance, it's only first kind of practical applications, but there's a great kind of hypothetical picture behind, which I'll explain later. Yeah, so Gromov-Witten invariants of manifolds, they come in two flavors. Yeah, you can define it for either for smooth, like it's infinity, compact symplectic manifold, or you can define for, I denote by the same letter x, by a smooth projective variety. And K could be any field. A priori, when the story started, it was field of characteristic 0. It could be any characteristic. And in fact, one can extend it now to arbitrary base, more or less.
Maybe a base scheme or something like this?
Sorry? Like scheme or maybe stack, yeah, something. Yeah, I didn't I will not talk about this extension, but in principle, one can extend for families.
Okay, and X, does it have to be projective, or it can be complete, or can it?
No, projective. No, projective, it's really analog of this symplectic. This proper variety, okay, I will do it in projective case.
Because you
I will use ample bundles, yeah. Yeah, in the case, and if my field is embedded to complex numbers, then these invariants are kind of the same or related, precisely. Okay. Yeah. So these invariants are something counting curves in variety, and in my lectures, I will deal only with genus 0 curves. So it's rational curves. Roughly. And what are these Gromov-Witten invariants? For any class. And again, you have two choices. If you do in symplectic case, you consider H2 of, second homology with integer coefficients. Or in algebraic case, you do something like this. I consider Chern group of one-dimensional cycles. You extend scalars to algebraic closure and mod out by algebraic equivalence. You do something like this, and then for any n greater than 0, you get a class E and beta, which belongs again, depending on situation, on H2 delta xn with rational coefficients, or in algebraic case, it will belong to Chern group with index delta of x and again we extend scalars and again make tensor coefficients. What is delta? Yeah, that's delta is called expected dimension. It's important formula which we should use all the time. It depends again on this n and beta, and it's defined like this. It's n plus, I'll write complex dimension just to keep both cases the same footing, minus 3, plus pairing, which I will denote by integral, first Chern class and the homology class beta. So it's some integer number. And sorry?
In the algebraic case, does it depend on the choice of the ample line bundle or?
No.
This is the meaning of my question. If it doesn't depend.
Yes, but then I want to make generating functions. I need ample line bundle. Later I will need ample line bundles. This guy doesn't depend. It's only existence of line bundles. And here you don't.
To define it, do they do it?
Yeah, I think it works in a proper case, but then will be a little bit trouble. Sorry?
But then there won't be ample line bundles.
No. This thing I think is still defined in a proper case when it's there's no ample line bundle, but it's not the case of what I want to study. Yeah. What one can say about these things? Yeah. First of all, for beta equals 0, the only non-trivial kind of non-trivial homology class is for n equals 3. It's A3 0. And the class is the following. It's the fundamental class of x embedded diagonal to its cube, and which belongs to, I'll write just into x of x cube. In fact, with integer coefficients, but I'll use always rational coefficients today. Okay, yeah, so that's class encoding this intersection of 3 cycles.
So I in beta is a specific class in general, or you're saying now I'm...
No. Yeah, the whole series how to define this class. I will not talk about this thing today. Maybe we'll talk in 1 week. So say just kind of informally what is going on. Kind of, again, really informally. It's not definition. You consider a set of all rational curves in X in class beta and with n ordered marked points or numerated marked points. It's something which maps, just if I get about curve to points, it maps to nth power variety, and in kind of ideal situation you consider class in Xn represented by image of this map. The fact that this thing has dimension of this guy, or let's say complex dimension, is greater equals than delta. So it sometimes it has larger dimensions than expected. But there is a whole theory of kind of virtual fundamental class, which maps in homology of degree to delta of this set, compactified in a certain way. And then E and beta will be image of virtual fundamental class.
So the virtual fundamental class is with rational coefficients.
Yeah, it's this guy with rational coefficients because this things we can compactify has some orbifold points. And you get class with rational coefficient, yeah. Yeah. And in algebraic case, it will be real algebraic cycles. And then you get these things. You get this collection of classes, and then collection of all classes, E and beta, okay, for n 0 and beta in this H2, or satisfy a bunch of axioms.
So rational curves which always connected you are going to take are.
Sorry, curves are connected, yeah.
But you allow this intersection, right? P1, 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 like.
Yeah, then will degenerate to some kind of like.
And the marking should not be on the single.
Yeah, I will talk. Yeah, details are kind of for today's lectures. Details are kind of irrelevant. Yeah, how it's exactly defined. It satisfies some bunch of axiomatics, and the most important is, again, I will not, or maybe I'll tell a little bit today, WDV equations where this thing stays for two twins, Verlinde, yeah. Witten digraph Verlinde. Yeah, it was something which discovered in early 90s. Some bunch of relation, and you need to some kind of notion like quantum product. Actually, this terminology a bit silly. And quantum connection. I will explain.
Who's the second guy in the list?
Sorry? Sorry, what?
The second guy.
Digraph, Robert Digraph. No, this is Witten.
No, I know it. Okay, so maybe you misspelled it slightly.
Digraph. No, no, I think it's right spelling this. And what I want to say about this? Yeah. It was maybe in 93, 94. Before the solved theory was constructed, with Yuri Manin we formulated properties of this Gromov-Witten invariance, formally some kind of like axioms, and WDV equations was one of axioms, this delta was another axiom, so it's symmetric. Yeah, those kind of plenty simple axioms, and that was some kind of last axiom which was kind of like orphan. It was motivic axiom. It said that in algebraic variety you get algebraic cycles, get class in each group, and it's kind of, it was not really play any role till now. This motivic axiom, in all kind of studies, people, yeah, it was some kind of stupid property, you have algebraicity, but it plays no major role. And what I explained that, in fact, one should be very, it's really central, for example, with this application to rationality, which I'll explain. And also I will say something a little bit about sociology of this theory of Gromov-Witten invariance. You see, it belongs to two worlds, kind of like symplectic topology and algebraic geometry. And in symplectic topology, it became kind of a major subject. Yeah, so it's I think there is now there was even more fundamental notion of Foucault categories also from middle of 90s, which supersedes this Gromov-Witten invariance. And in symplectic topologies, that like everybody is aware, knows Gromov-Witten invariance, this Foucault categories, and that's kind of the core of the subject. In algebraic geometry, although it looks like you ask question in algebraic geometry, how many curves of certain degree pass to some points, it's it's placed really, it's kind of completely isolated subject. So most part of algebraic geometry is completely happy without knowing this about Gromov-Witten theory. Okay, that's who is interested how many curves of degree 10 pass through whatever 33 points on P2, some huge numbers. Okay.
About the compatibility of the method in symplectic geometry where you deform the symplectics.
The whole thing's a deformation invariant.
No, but when you define it, I forgot now. I think in the algebraic geometry case there was a paper of Fanteshi or so. Anyway, there was a paper on virtual fundamental class.
Yes, yes.
Is it proved?
Yes, yes. It's, people compared this definition of symplectic geometry and algebraic geometry. Yeah.
Okay.
Yeah. So it's all compatible. Yeah. But I want to say that it was kind of really remote subject and kind of from outside algebraic geometry, not of great interest. Who knows how many curves? Yeah. Yeah. But it's kind of really kind of sad situation because I think it's really core of algebraic geometry. At least from this now applications to birational geometry, it's kind of like practical things, but at least people in birational geometry or minimal model program should really learn the subject. And otherwise, of course, one can live without it. Okay, now just before going further, I just want to kind of describe briefly two examples how Gromov invariants look like and what they really calculate. So first example will be when my variety is P2. And yeah, this belongs to class of what's called Fano varieties. When anti-canonical class is ample. Positive means bigger than 0, it means it's ample. And then we can associate some numbers counting some curves. Would equal 1, 2, and so on. I say what is CD is the number of rational curves, actually with nodal singularities. In P2 of degree d and passing through generic 3d minus 1 points. And one can make a little table with its numbers.
So is it the case that generically, indeed, when you count the dimension is the expected dimension?
Yes, yes. In this case, you get expected dimension, yeah, and yes. Yeah, it will be really kind of naive counting, yeah, in this case, yeah. Like, for example, if I have 2 points on P2, there's only one line passing through points. Yeah, you get 1. You get 2 points, you get 1 line.
And the curves are embedded in also, or not?
Curves are embedded with nodal singularities, self-intersecting, yeah.
Okay, but so it's not a map from a curve to P2, but just embedded in...
Embedded, yeah. Kind of immersed curve, yeah. Immersed curve. Okay, maybe I will explain to what's going on. It's not so complicated. Yeah, if we get 5 points, yeah, then it will be unique quadric. When you get 3 points and consider whatever, now 8 points, degree 3 curve, and consider, I cannot really draw 8 points, then there will be one parameter family of elliptic cubic curve passing through this. And among this cubic curve, when you get curve with one nodal singularity, there will be 12 of them. In this one parameter, you get one parameter family of cubic curve passing through 8 points.
And then there are 12 in general, there are 12 nodal ones.
Yeah, 12 nodal one, yeah. Yeah, then there are numbers which you probably don't know. For degree 6 you get 620, degree 4 you get 620, degree 5 you get whatever. Yeah, you get this numbers. Yeah, so what? How it's related to the Gromov-Witten invariance? You take beta is equal to d times class of P1, and n equal to 3d minus 1. Yeah, now let's make this calculation. What is delta? Delta is what is n? Yeah, 3d minus 1 plus dimension of my CP2 is 2 minus 3. Okay, and plus I think 3d. Why 3? Because first chain class of the tangent bundle, which is anti-canonical class, is 3 times kind of Poincare dual to the class of a rational curve, hyperplane section. And so what you get here, you get 2 times delta is equal to 2 times 3d minus 1. So it's equal to the dimension of x to power n. So it means that the space Ux has fundamental class equal to the dimension. You evaluate it intersect with zero-dimensional kind of point, and you get some number. This will be this number. And what one can say about these numbers? This WDVV equations gives the following relation. For d, any d at least 2, what one gets that the CD is equal to the sum over d1 plus d2 equal to d. And multiply by some combination of binomial coefficients. And so here you see some recursion. If you know C1 equal to 1, just put this input for this recursion. You can calculate step by step all CD and get these numbers. So it's uniquely determined. This equation of all CD. And what I would say is Gromov-Witten invariance of all the drenching series is essentially reduced to these numbers. And so we get this sequence of numbers. And this recursion eventually is related to some specific solution of Penlevé-6 equation. Okay, that was the first example where this whole thing started with the calculation which I made, this calculation I made in the early 90s. Now I go to another example. So it will be example number 2. So X will be, it's kind of the most famous example in the subject is X is a smooth quintic threefold in projective space. Yeah, so it's given by some equation, homogeneous equation in 5 variables. Get homogeneous polynomial degree 5. And then, yeah, that's the class when canonical class is 0. It's called Calabi-Yau variety. Yeah, again, we have a sequence of numbers for d equal 1, 2, so on. I take beta is equal to d times class of projective line. In fact, this quintic threefold has plenty of projective lines. You'll see how many in a minute. And n equal to 0. I get no marked points. Yeah, then let's make this little calculation. Yeah, this formula kind of like sine square plus cosine square is this formula for me in the subject. I have always to do this calculation. When dimension is no points, here's 0, 3 minus 3, 0, 0 plus 0, you get 0. Yeah, so these things are isolated. You should get kind of number of rational curves here, kind of morally this, let's say GVD will be this invariant, which is just a number, which is E whatever 0 beta, which belongs to H0 of something of nothing. I think of 0 power of H0 of point. Yeah, so it gets its Q. So I get sequence of numbers. And again, I'll make table. So just denote these numbers by GV Gromov-Witten invariance of in degree D. Yeah, instead of this I0 or whatever. Yeah. First, we start with lines, curves of degree 1, and I told you there are many of them. That's exact the number. How many? 2,875. Okay. Then for degree 2, maybe just degree 2, you get fractional number because the definition is slightly complicated. There are some orbifold, and in degree 3 you get even, yeah, numbers are completely okay. Yeah, so it doesn't look like a number of curves. You don't have 1/8 curve. Yeah. There are other numbers called GVD, and this stays for Gopa-Kumar Waffa. It's slightly different numbers. The first one is the same. The second one is this guy, and the third one is yeah. So these are rational numbers, these are integer numbers, and the relations between one number and another is the following. is Gromov-Witten of D is equal to sum over k dividing D. And these numbers equal to actual number of curves in generic of rational curves in generic quintic threefold X, but only for small d. I think it's maybe up to 4, which had this still as a number. But then you get a problem. For d equal 5, these curves, even in generic Calabi threefold of sufficient large degree, they come in families. They are not isolated. Still, numbers which you get here are integer. And now maybe I'll try to describe you. Sorry?
For what class of spaces is this properly defined mathematically?
Sorry?
The second list of numbers, the go-go.
Yeah, the story is it's a bit involved. Yeah, so the first, when you get map for rational curve, you consider kind of multiple. You consider have other maps from rational curves composing with multiple covers, and then these multiple covers contribute to this degree k contribute to this 1 over k cube in this Gromov-Witten invariance. So there's idea to remove this multiple cover story. Then there was interpretation of some kind of BPS counting, so it will be intrinsically integer number, and it's come from in various flavors like Donaldson-Thomas invariance. There was no really proof that it's this coincides with Gromov-Witten invariance. And for example, integrality for the, I will write some formulas how this Gromov-Witten invariance looks like. In a way, Gopakumov for integers. There was a proof which we have with Albert Schwarz and Vadim Vologodsky using periodic methods, maybe except prime 2 and 3. But recently, I think there was a result by John Pardon. It's reduced equivalence between Donaldson-Thomas and this Gromov-Witten invariance. So it really gives a kind of intrinsic proof that numbers are integer.
But they're defined for the same class of input data, like for compact C infinity.
No. Gromov-Witten invariance is only for 3-dimensional Calabi-Yaus. And in fact, here there is a point which before just erase. I said that in algebraic case one can make kind of fine accounting. One consider like connected components of Chow groups. And for 3-dimensional Calabi-Yau, it's really interesting object. It's infinitely countably generated abelian group, like Claire Voisin proved it. Yeah, and with finite counting, we really don't know what is going on.
So what is infinite?
This set of connected components of Chow 1, it's infinitely countably generated group.
For this quintic?
Yes.
So here, in general, you're looking characteristic 0.
And characteristic 0, yes, yeah.
So what do you mean by connected components in Chow 1? It's a group.
It's a group, yeah, but if you have algebraic equivalence, they're related by continuous. Yeah, it's a group, but still like an infinite unit of algebraic varieties, and you take connected components, still get a group which will be countably generated. Even your field is uncountable.
This formula GWD equals this.
Yeah.
How general is this formula?
It's just for this 3-dimensional Calabi-Yaus.
Oh, for this particular 3-dimensional.
No, for any 3-dimensional Calabi-Yaus.
And for any D.
Any 3-dimensional Calabi-Yaus.
Okay, 3-dimensional Calabi-Yau and any D.
Yeah. Okay.
In the simpler enumerative problem on P2, is it to have the nice situation, do you need characteristic 0? Or, because I think like for the family...
Yeah, okay, let's do characteristic 0. In characteristic P, nobody touched yet, I have to say. There is theoretically a definition of Gromov-Witten invariance, but nobody.
I'm saying just the geometry of a family of cubics in low characteristics is different.
Yeah, no, the story is the following. If one can define Gromov-Witten invariance in characteristic P, but also in mixed characteristic, and independence implies that for varieties which can deform to zero characteristic, you get essentially no new numbers. But for varieties which you cannot deform to zero characteristic, should be something else.
That's the statement that you have the numbers, that is the multiplicities are one.
Yes, yeah.
This is something special.
No, it's true. Okay, let's don't discuss characteristic P because it's not subject of my talk. Yeah. Okay, so what are formulas for these numbers? Yeah, you construct. It's a bit long formulas. So for variable t with real part very much to the left plane, I define f of t. So t is a complex number. I define as 5, 6 t cube plus sum over equal 1 of this Gromov-Witten invariance d exponent dt, which using this relation one can write as Lis 3 is usual three logarithm. Function. And what is mirror symmetry prediction for this series? Mirror symmetry prediction is the following. You start you define four series which is polynomials in log z and series with coefficients in series in z for I equal to 0, 1, 2, 3 in the following way. You just if you take sum of this multiplied by powers of epsilon, then it will be this guy.
So this formula you wrote is still for Calabi-Yau threefold.
It just no, yeah. What I wrote it's just for this example. Yeah.
Right.
Okay. I just do this example. Nothing.
Okay.
Nothing more general. Yeah. So get this this series and what are these guys? Psi 0 is such sum. Psi 1 is psi 0 times log z plus another sum. And so on. Yeah, so I get four series and all solve equations d4 psi is equal to 5 times 5d minus 1.
What is the exponent of z in the series? Z to the n plus?
Epsilon. And you expand in epsilon, you get z to power n plus log z epsilon. Yeah. I get this hypergeometric equation of degree 4 when d is z dz. Okay, so I get these things. And then what is the mirror symmetry prediction is the following. I get this guy, substitute psi 1 over psi 0, and then I get yeah. Okay. Yeah, that's how mirror symmetry kind of Gromov-Witten invariants look for this quintic threefold.
What is that?
Sorry?
What is F?
F? F is this?
Ah, the one.
Yeah. Yeah. Okay. So, yeah. So that's psi 1 divided psi 0. If you consider ratio, you get log z plus some series. Yeah. Now, so this was proven by.
What is the meaning of the psi in terms of? Okay, this is. The psi's are kind of the solutions of this differential equation. This is the basic, the fundamental solution is given by the psi.
Yeah. This is also all psi are solutions. All psi I satisfies this equation. Yeah.
This is
Yeah. So that's gives you this calculation, and then calculate these numbers, and that's the picture. That's the whole story. Yeah. So the whole thing was. It was more than 30 years ago, and maybe about 95 or something like this. Sasha Giventhal proved it, and yeah, you see that you can compare two situations. Here, in the case of P2, we use WDV equations. And what happens in this case? Those WDV equations gives no constraints whatsoever. Yeah, so the Gromov-Witten invariants, besides this kind of initial term, which is come from intersection theory, are determined just by arbitrary sequence of numbers with no condition whatsoever, but still there is some nice differential equation controlling the whole story, which kind of comes from something else. It's not WDVV.
Is it n by k or 1 by k?
1 by k.
That's 1 by k.
Yeah, it's kind of harmonic sum. Yeah. Okay. So, so these are two examples to get you a feeling what is going on, and now I'll just try to formulate some general picture statement. So now finish with example. Now Let's introduce two main ingredients. Let's start for simplicity. I just don't want to really go to complete generality. Smooth projective varieties over complex numbers. It is or symplectic manifold. It's part of the story. Lives in both worlds. So I denote by just H. It will be sum of two even and odd parts. It will be just by definition cohomology of manifold with, let's say, complex coefficients. And I consider this because decompose the way odd and even part as a super vector space over complex numbers. And then I can treat it as complex analytic supermanifold. And what I want to define, I want to define some like kind of temporary goal will be using Gromov-Witten invariants to define some even function, even holomorphic function, which denoted by F0. It's more or less related to the series F, which I drew before, on a domain in even part, and it will be functional on supermanifold. It will be also functional. And in fact, domain, what is important, should be non-empty and connected.
So the supermanifold is just the even part equipped with some superstructure.
Yes, yeah. Algebra functions will be this.
So those are the functions on the manifold.
Yeah.
Those are the super functions.
Yeah, so functional supermanifold. Yeah, just it's. But to define domain, it keep only even part. Yeah.
So it's the point I just said.
Yeah. On a domain, yeah, with. Yeah.
It just said is a point.
Yeah. No. Now, so I'll write kind of. Formal for value at some point. And as usual in supermanifolds, point gamma sitting in, yeah, I'll write kind of H not writing even. So one way to say what is a functional supermanifold, you consider function depending on some Artin superalgebra, and I will not go to the details, but just imagine that it depends on some superparameters. So write gamma, if you get point in this cohomology space, it has degree 2 component and degree not 2, which we can decompose in. And this guy, not 2, includes all odd numbers. So this includes all fermionic directions. And the function f0 of gamma is defined like this. It's 1 over maybe 3 factorial integral of gamma cube plus sum over beta not equal to 0 exponent of integral of beta of gamma 2. Gamma 2 recall this class in second cohomology, so can evaluate on second homology. And then multiply by sum for n greater than 0, 1 over n factorial. And then you integrate over this Gromov-Witten homology class. What you do, you get part of degree non-2 and make exterior product of n copies of this guy.
So that's factorial 3 root or what is
3. maybe 6 is equal to 6. Yeah, okay. Yeah, in fact, you see it's almost the same expression here because we integrate over x, or it's the same we integrate over diagonal class in x cubed times the product of 3 copies. Yes, it's more or less the same formula. So the conjecture, it's still open that this gets absolutely convergent in some domain, in some non-empty constructible domain, when, for example, when gamma 2 belongs to I use Hodge decomposition. You have H20 and H02 pluses on a curve, plus yeah, gamma 2, on gamma 2, for convergence, the restriction should be on only some small part. In H20, H02, it plays absolutely no role because the curves are algebraic. They will not contribute to the pairing. When you consider imaginary, for pure imaginary form, it gives things of absolute value equal to 1. And to get convergence, to get the things rapidly decrease 0, it seems it's necessary to, it's kind of sufficient to say that this part in H11 and H2 real form of types H11, it can really contribute to integrals over curves, belongs to kind of shifted negative Keller cone. You consider omega 0 at some sufficiently large Keller class. So it will not converge, so you get 0 and you kind of like shift things here. More precisely, the domain should be certain convex body of convergence. Even in the case of quintic threefold, this essentially will be like when t is negative number, sufficiently large negative number, this series above will be convergent. But then it has, it's thought to be converged at some point, which one can calculate through all this change of variables and this complicated business. Yes, so we cannot really say for sure at which symplectic form it should be converged. For sufficiently negative one, it should.
So, but I'm absolutely convergent. So this series, if not no, what is absolutely convergent? I don't quite follow.
Sorry, absolutely convergent. It's convergent if identified and gamma t belongs to kind of like bounded ball. You can see the even part of not two, and only even part.
But there you allow the odd part also?
Yeah, for odd part you should kind of think it's like form parameter. Yeah, in gamma non equal to you allow odd part, yeah, and then it's like usual in supermanifold.
Why you say bounded ball?
Bounded ball, yeah, again, in the case of CP2, for example, when you get these numbers of things divided by n factorials, it will also have exponential growth. If you make geometric series, you get some finite radius of convergence.
So it is not convergent when the ball is too large?
Yes, it's not convergent when the ball is too large, yeah. Yeah, some ball containing 0.
I'm sorry to interrupt you, but if gamma is an odd class, this integral will be 0 because
No. You get many odd classes. And also you consider this like functional supermanifold, so it makes perfect sense.
but I and beta only lives in the even class. It's a homology class.
Beta, yes, but this here you get product of odd classes, so you can get even class. Yeah. So you get.
So the conjecture says that this series is absolutely convergent provided
Yeah.
gamma t belongs there and gamma not 2 is in some bounded bound.
Yes.
that the conjecture?
Yes. And fermionic variables are kind of arbitrary. Yeah. For them, they don't put
And fermionic variable means the odd degree.
odd degree terms.
That's
Yeah.
what
Yeah.
you mean.
Yes. Yeah.
So of course this series is composed of different, you have beta, sum of beta, and okay, so you take absolute value everywhere, and then this should be
Yeah.
absolutely and uniformly and compact.
Yes. Yeah.
So you say that for like the case of P2 is that it is known or
Yeah, it's known in all concrete examples when we can calculate something, but it's not yet proven. Yeah, and it's actually, I think it has more chances to be proven in algebraic geometry case. In symplectic geometry case, it's more complicated, but still, there's no general result. So the convergence. So what I would say about this convergence, I'll kind of assume for today's lecture, just to simplify exposition, and it can be circumvented. Yeah, so using some non-Archimedean fields, one can avoid the question whether it's convergent or not. Yeah. So now if you have this, now we have this function on some domain. I'll try to define what is quantum product. It actually will be or quantum multiplication. Actually, it's a product depending on point in this domain. Yeah, let me denote actually domain somehow. Star depending on gamma. Where gamma denote domain, maybe denote domain something like ux.
So you are fixing some domain in
Yeah, I kind of don't really specify it, or maybe germ of domain to infinity, something like this. Consider things where this thing is convergent, and take point with even part belonging to this ux, and then the star product will be on a it will be multiplication on tangent space to my domain, but because it's open domain, the same as tangent space to all cohomology space, and all cohomology space because I find it's just its cohomology. Yeah, so it will be a multiplication on cohomology of my variety in practical terms, but geometrically one can try to think it's actually multiplication on tangent space. And how it's given? What's the formula for this multiplication? We consider third derivative at point gamma. Because it's affine space, one can speak about high derivatives intrinsically of functions. It's a map from tensor cube to C, yeah? Or we can, using this identification, write as map from H equals H to C. Yeah? Or using Poincare duality, so H is isomorphic to dual space, canonical way, we can rewrite as just by linear operation on H. And these things I will denote by star gamma. Yeah. Yeah, so this basic fact, it's actually what WDVA equation says, that star gamma gives commutative associative unital product on this tangent space. In fact, because it depends on point on unit on vector bundle. It's a family of products.
So you are taking partial derivative along some direction?
All directions.
Oh,
all directions.
Okay, so that's the, okay.
Yeah.
Okay.
So this is because you had H1 and H2, so the even and odd part, so now this is due to the super.
It's in super sense, yeah. Super, yeah. Super.
So the partial derivative is taken even in the odd,
No, in all directions, yeah. Even ordered,
odd direction.
including code, yeah.
I see.
Yeah. So that's this quantum multiplication. And if you look in the formula, I kind of already removed things. This this formula, when your class in second homology goes to minus infinity in Carrier class, these things which goes very fast to zero. You get only zero. So you left with this triple intersection, you get cubic, when you get things, you get classical cup product in the limit. So it will be deformation of the classical cup product when your Keller class goes to minus infinity.
The unit is the usual unit?
Unit is usual unit for all at all points, yeah. Yeah, so I get this object, and second ingredient which I introduced before, little break, it will be what is Euler vector field. Actually, it's even vector field. It's section of tangent bundle, holomorphic section, and I'll again write kind of loosely what is the value at any point, and if it's odd variables, you introduce some formal parameters. It will be the following: is first Chen class of tangent bundle plus deg minus 2/2 gamma, which is element of H, which is a tangent space gamma to U. The degree is a degree operator. It's sum over j from 0 to 2 times dimension of x. And you do j times identity operator on j's cohomology of x. Yeah. It's some grading operator. Yeah, so there is multiplication. And another fact, it also follows from kind of all grading considerations that this Euler field preserve the product Okay, so now I think I make a little break for maybe 5 minutes. Okay. Now, so what I claim that this subject one can use as a black box, like in the black geometry, Ital cohomology. It's kind of like complicated theory, yeah? But you don't really care about details. You can use as a tool. And here's a second. Yeah, start with some general structure result for the structure, which I didn't name yet. Yeah, so pick any point in just even part of cohomology. Actually, maybe in U even. Sorry, when I speak about domain, I want to speak about in even cohomology, I speak only about even part. Yes, so I take purely even point. Then it gives the operator. Again, even operator. Namely, consider value of Euler field at this point. Its element on the tangent bundle, and then we can multiply using the product. Depending on this point on the tangent bundle, I get some operator from the tangent space to itself. Okay. This tangent space has even and odd part as well, so I get like two operators, technically, even and odd part. And then choose a finite collection of disjoint disks the alpha in C such that the spectrum of this operator, which I denote just simply EU gamma, this operator, whatever, belongs to this union of disjoint union of disk. Yeah, so how it looks like, I have in C several disks and consider surrounding my eigenvalues. Then obviously for all gamma prime which are sufficiently close to gamma, because the open, actually disjoint open disk, maybe I'll say. Because these are open, we get the same things. We have spectrum of EU gamma prime also belongs to this union of disks. Sorry. Yeah, I started. Okay, maybe I'll repeat for people who a bit late. Yeah. I'll just repeat. Sorry. And I'll start with the decomposition theorem. So you pick any point in an even part of my domain, just pure even point. Then we get even tangent vector, this value of Euler field. Then we have multiplication. Consider operator multiplication by this even vector. Get some even endomorphism of the tangent bundle. So in fact, there are two endomorphisms of even part and odd part. There are kind of like two operators here. And they have some eigenvalues. And now choose a finite collection of disjoint open disks.
So you have operators on what?
On tangent space.
At gamma.
At gamma.
I fixed gamma.
Euler of gamma.
And then I multiply by kind of. I consider operator multiplication in the algebra.
Okay, so then you have choose a finite collection of disjoint open
Disks such as spectrum is contained in this disjoint union.
disjoint open this is a spectrum of Euler gamma containing.
Yeah. And then the claim that because disks are open, if I deform a little bit gamma prime, then this again in even part, then the spectrum will be still contained in this disjoint union. Yeah, it's no. And then you see that, and then it implies the following: the tangent space is decomposed sum of pieces labeled by disks. In fact, this summons here I consider all non-trivial summons here in this decomposition carries a structure of, again, unital, what was this, commutative associative unital algebras. So this thing gives me decomposition of my algebra by direct sum of subalgebras.
So why they are closed under the algebras?
It's this property of any finite dimensional supercommutative algebra. If you have any element, even element.
If you have any even element, then its eigenspace or the generalized eigenspaces.
Yes, they'll be automatically. We decompose spectrum in several disjoint components. Because if you have different eigenspaces, you decompose spectrum with algebra in the union of disjoint components. Yeah.
But this is defined only in a neighborhood of gamma.
Only in the neighborhood. On the neighborhood. It's not only in the neighborhood. Yeah. So I got this kind of.
Okay, so the identity is a projection of the identity into.
Yes, yeah, one can make projectors, yeah. One can apply certain polynomials to this element such that polynomial equal to 1 in a sufficiently large formal neighborhood Z of eigenvalues and 0 otherwise, and then you get commuting projectors. Yeah, so what goes on? But before going to this algebras, we see the tangent space in any point decomposed in you get subbundles. You get many subbundles. And what goes on here in this decomposition theorem is that these subbundles form foliations, they are integrable, and these foliations do commute. You get commuting foliations. And what precisely this decomposition theorem says that under these choices, the claim, it's actually some construction form from the story, this germ of U at point gamma is canonically together with product on tangent bundle and Euler field, yeah, canonically splits in a product of germs. As product of germs of some other varieties, kind of like U alpha. It's some maybe base point to denote gamma alpha. With some product depending labeled by disks, and Euler field also labeled by disk. And such that spectrum here alpha at some point close to 0 belongs to this disk alpha.
These are commuting in what sense?
Commuting foliations, yeah, because if you get many foliations, you get maps to some spaces of leaves, yeah, if you get foliations. And all these maps are organized to get like product of some variety and projects to just one product of all factors except one. This will be foliations, yeah.
But it has odd degree also, right?
Odd degrees as well, yeah. But foliations, yeah, but foliations also have always even part as well, because these algebras have units, and units are even. So even part is always non-trivial in this story. Yeah. Yeah. So you get kind of like product structure. Yeah, that's a simple formal result. And now I'll go to something.
You're not assuming semi-simplicity.
Sorry?
You're not assuming semi-simplicity.
Assuming what?
Any kind of semi-simplicity. Semi-simplicity.
Oh, there's no simplicity. No. Yeah, it still holds. Yeah, just.
But this decomposition is unique, right?
It's kind of unique if you choose these disks. Yeah. Then yeah.
The choice of disk is also in some sense.
No. For different choice of disk, you get finer. Finally, you can go to different eigenvalues to get the most finer decomposition. Yeah. Yeah, but if you choose disk, you get some decomposition product. Yeah. It's with these choices you make this canonical decomposition in the product. So then I'll go to some blow-up conjecture, which is it like pretty yeah, it should be much earlier, but it's only 4 years ago I proposed this conjecture, which deals with the following situation. Yeah, this is kind of general pictures. If you have this Gromov-Witten invariance, you get this product structure. Now imagine the following thing. Suppose X contains a smooth closed submanifold, not necessarily connected, of pure codimension R, which is at least 2. This could be disjoint union of subvarieties. Yeah. And then I define by X tilde the blowup. It's again automatically smooth projective variety, yeah? And it projects to X. Now I consider the following point in cohomology of X tilde of the blowup.
So we are in the algebraic situation.
Algebraic situation, yeah. The whole story can be formulated symplectically, but I don't want to go.
Algebraic situation right now.
Yeah, algebraic situation, right, yeah. Yeah, and over complex numbers to simplify life, yeah, but the whole story as well. I take class in second cohomology of the following form. I take minus some constant multiplied by pullback of class of omega 1, 1x and minus omega 1, 1 x tilde, where these guys are Kähler forms on x and x tilde. So I get this class depending on C, on number C. And now this kind of like direct calculation, don't do it today, but just give the answer. Then for C real and very large, then spectrum of this operator it's contained in the following gadget. So will be disk around 0. Will be several disks around some points. Will be some kind of regular d minus 1 gone and 0 in C, and you take regular gone certain size depending on this omega x tilde, and you get this essential roots of 1 and eigenspaces, and yeah, so you get these eigenvalues are inside these pieces, and all eigenspaces are isomorphic to what? Here it will be cohomology of x, and all the rest you get cohomology of z, copies of cohomology of z. In fact, what goes on? That if you make blowup, then cohomology of a z-graded space of x tilde is isomorphic cohomology x plus direct sum of r minus 1 copies cohomology of y. Yeah, so you get this decomposition of eigenvalues in this limit.
So D is Z. You mean Z, well, not Y, but Z?
Oh, sorry, Z, yeah, sorry, yeah. Yeah, but as Z graded spaces, as Z2 graded spaces. Or super vector spaces.
So the regular D minus 1, D is R or?
Oh, sorry, R minus 1, yeah. Misprint, thank you.
And the regular gone is at the roots of unity? Or?
Roots of unity multiplied by some constant, yeah. And constant depends on this omega 1 x tilde. It's a real constant, yeah, real constant, yeah.
So this omega x11, so you are putting it a particular embedding, because unless you put your variety is just a projective variety.
No, it's projective, it's a property. I don't choose projective embedding.
But then omega x11, what does it make sense?
Oh, no, it's some Keller forms. It's there's no specific choice here.
Okay. So you are fixing one Keller form on
X and another one on X tilde, yeah. There's no compatibility at all.
no compatibility.
No. Yeah, so it's so I didn't really formulate yet the conjecture. Maybe I can do it. Have enough space on the previous board.
So this is still part of the conjecture that.
No, it's not part of conjecture. I didn't formulate it yet. I just make some preparations, but not formulated. So what is kind of looks completely natural, this formulation of conjecture, that if we apply decomposition theorem, some domain in in this ux tilde get some domain in ux tilde when you approach, consider neighborhood of such points, yeah, is decomposed by product of some varieties with multiplication on tangent bundle and Euler field. And these guys should be domains in ux and in uz r minus 1 times. Yeah, that looks completely natural because these guys have the same dimension. And yeah, so the story was the following. I gave a talk about, and from this conjecture one can deduce this rationality stuff. You'll see in a few minutes how one can deduce the whole story. Yeah, so it was kind of like very gentle time at the moment. I visited Moscow. It was before COVID, before all disasters. Yeah, I visited Moscow and gave a talk here. And it was Hiroshi Iritani, a guy from Japan who was on this conference. He listened my talk, and he now proved it. So it's actually theorem by, and he proved really this sum of this here. He proves it's kind of like formal version. No assumptions on convergence. But I'll explain that it's kind of completely harmless problem, and one can apply this result kind of like assuming it's convergent and so on.
Can you state the conjecture again?
Sorry?
Can you state the conjecture, the form?
No, it's a bit long. I don't want to do. For my lecture, I assume this convergence, and when I assume convergence, that's literally what I state.
No, what have you written there? I can't understand.
So the conjecture is that it's the decomposition theorem gives a product of my domain in a product of again some complex supermanifold with product of tangent bundle Euler fields, and these guys are domains in these things related to ux and uz. Yeah, but formal version it's a bit longer to formulate. I don't know how to do it. Yeah. So now we can, from this just result, one can really.
So the decomposition, just to be clear, decomposition theorem gives a decomposition like that.
Yes, it's. Yeah, but claim these factors are not arbitrary varieties with product tangent bundle, but exactly.
But it's like, okay.
Yeah, exactly these guys.
So, but that's part of the theorem.
It's part of, it's a theorem, yeah, it's now a theorem, yeah.
Yes.
Modulus these convergent issues, which I
see.
minor, yeah. Yeah, now we should go kind of applications to rationality. And this comes kind of really for free. Just you don't have to know all technicalities of all this machinery. The applications are three, but before I need little preparations. Just let's suppose we have vector space over Q and decomposition of direct sum in a classification in components such that it is a direct sum of pure polarizable hot structures. So I don't say it's pure because it's sum of things of different weights. Direct sum of pieces of different weights. Then we define for 6 kind of like Hodge part. Hodge cycles, this will be intersection of V it will be a space of Hodge cycles. And now define a category I don't know, like C, whatever. Objects are such guys, and home from the category to from I'll just lose it right V1, V2, skipping this all Hodge decomposition, will be I take tensor product and consider Hodge part. Now, so it's what you get. You get semi-simple tensor category, and what's called with fiber functor, with tensor fiber functor, to vector space over Q if you get about this Hodge decomposition. And then, by general reasons, it implies that C is category of representations of G, where G is a pro-reductive algebraic group defined over rational numbers. Yeah, so it's kind of like version of Mumford-Tate group.
So here you must work with just even, not super vector spaces, just usual.
Yeah, no, I work with usual, yeah. Yeah, just at the moment as usual.
But when you have this Hodge thing, is it only kind of even cohomology?
It's only an even, yeah.
But the fiber factor is taking taking the even part? No, the fiber factor is
Fiber factor to take V.
V itself.
V itself, yeah.
But V itself is
Yes, yeah, okay. I'll just tell you in a second what you want to say, maybe. Yeah. Yeah, so this group has two things. There is element epsilon in the center of the group, and you have kind of rational point with square is equal to identity, such it acts, its epsilon acts by -1 2 times P plus Q, okay, by weight in any representation.
okay, this is the way to, because I wonder in the tensor structure.
Yeah, I will go to in a second. I will say what I said. It's pro-reductive group, and with central element which is square is equal to identity. And also, if consider complex points of this group, it contains C star, namely lambda in C star acts on VPQ by lambda to power P minus Q. And -1 is it contains -1, which is epsilon. Yeah, it's the kind of formal object, and if we have any variety X, that's a smooth projective variety, then this then cohomology of X as is super representation of this group G such that epsilon acts as parity. Yeah, if you get group with central involution, then one can make a new category of super representation when epsilon goes as parity. And that's what really goes on in geometry. Okay. So I get the super representation. And if you consider invariance, cohomology with rational coefficients. And when you consider fixed points under this action of the group, it will be exactly space generated by Hodge cycles. Get whole Hodge classes, which are potentially, if you believe Hodge conjecture, which I don't, that it's algebraic class represented by algebraic varieties. Yeah, it's kind of personal. Yeah, I don't believe it. Yeah. Sorry?
I want to ask for the nth time the question about the tensor structure. So the tensors, do you have commutativity and associativity constraints, but on when you consider super vector spaces,
Yeah.
you have natural commutativity and associativity.
Yes.
But then you get not a fiber factor to vector space.
Yes. No, it's a different category. I claim that there are kind of like two categories. You have categories fiber functors to usual vector spaces, but then you get this pro-reductive group. Then you can consider super representations. It's another category, and this another category consider again subcategory when epsilon acts by -1 to the parity.
Yeah. So, but in this category, the tensor structure is such that.
Like in super mathematics, you put.
No, but you said that you have a semi-simple tensor category.
Yeah.
Given by those.
Yes.
Fiber factor to vector spaces.
Yes.
But the tensor structure is the super commutativity constraint, or the.
No. Here's nothing super here.
So here you take just.
Usual tensor product, yeah. Yes, usual commutativity, yeah.
Okay. And so but when you compare to geometry, like the cohomology of x cross y, the cohomology of x tensor, the cohomology of y, you are obliged to use that.
Yeah, I twisted using this epsilon and make a new category. If I have a group, I can make, when I have a group in central element, I can make a new category, super representations, when epsilon acts by -1 to the parity. Okay.
But G is a honest group, not a super.
G is honest group, yeah. Actually, no, it will be better. Just a second. Yeah, now Now the story is the following. I have this group of rational numbers, yeah? I change scalars from Q to C. Extend scalars to get algebraic group over complex numbers. And the claim is that 6 acts on of course it's acts on cohomology of X. Any variety, yeah? And also it should act on domain. And the action preserves everything. Function.
Why should it preserve a small open set?
Sorry? Group?
The group is a global object.
Yes.
Why should it preserve a small open set? UX is a small open set, right? Its Lie algebra will preserve. But why should the group preserve?
No, the story is the following. It's at least Lie algebra preserves, yeah.
The Lie algebra definitely preserves, but I don't see why.
Yeah, but in fact, for these convergence issues, if one look carefully at the end of the day, these things, everything will be well defined, will be invariant on the whole group. Yeah, I said the unit small disks. Yeah, right. Yeah, it's okay. It acts locally. Okay. Acts.
Yeah, right. That's locally.
Okay. Yeah, it's maybe just say like this. I agree. Yeah, and then it preserves everything. It preserves this function f0. Product, Euler field, because what we use cycles I and beta, yeah, the algebraic cycles, and they're given by Hodge classes, and then automatically everything is okay. Yeah. Yeah. And now I'll give some definition. Because this group is related to something like Mumford-Tate group, it's more or less the same as Mumford-Tate group, except this forget about weights. It's kind of like Mumford-Tate or just MT spectrum of my manifold. Yeah, that's a key definition on which everything is based. Is the following. It will be finite collection with some multiplicities of, yeah?
I'm sorry to interrupt you. Do you really mean preserves or it one? See, because the odd part of the cohomology.
It's acts, yeah. No.
Won't it multiply by a scalar?
No. It just preserves everything. This group.
It preserves the composition into even an odd part.
In odd part, yeah, as well, everywhere, yeah.
I see, even in the odd part.
Yeah.
But it mixes the different components of the even part of the.
Yes, it mixed. In odd components also mixed. Yeah. Yeah. No. It's no, the group doesn't mix. If it preserves each cohomology subspace, it preserves. But different like H0 and H2 of P1 are isomorphic, as are both trivial representation for this group.
So each HI is preserved under the group.
Yes, it's H preserved. Yeah.
Yeah, because it's not a super group. It's just a.
Yeah. If you go, I don't know, if you like Eliadic representations, yeah. Just for a second. You can have Galois group of K bar over K goes to GL1 QL. You consider kind of italic homology of H2 of tal of P1 with Eliadic coefficients, yeah? And now you can see the kernel of this map it acts on Eliadic cohomology and it maps to whatever QL points of my group.
Is it for large enough field or for all?
I don't know, for any field, yeah. Yeah, consider number field, say, it really does matter.
Because sometimes there is a result that compares
Yeah,
when you take a sub-finite index. So
yeah, okay. No, I don't want really to go to this stuff, yeah. Yeah, so the command for spectrum is find a collection of what? Of isomorphism classes of non-trivial, and here there are two choices. You can have like super or ordinary representations, representations of my group. Again, I change scalars to C, so I get a little bit more than I think so rational numbers. And super, but super when epsilon x is to -1 to parity, such super representation can be identified with ordinary representation. So it's two different languages for the same things. But actually super a little bit better. The property is that each representation, for each representation, there exists GQC invariant structure of a unital commutative associative algebra, superalgebra. And particularly this representation will be always reducible because they have contain trivial representation coming from the unit. Is always a summand. So what we deal with reducible representations. And we get isomorphism class of reducible representations. And how it's defined? Definition. Consider kind of like fixed locus. It's kind of like Ux even. I consider in my domain, consider only combination of Hodge classes. Yeah, so by definition it's the same as Ux even intersected with complexification of the space of Hodge classes.
why write equal to UH even?
Sorry? Sorry. H to even G. This G invariant part. Yeah, it's ordinary. It is purely even. Again, non-empty, connected, smooth, complex manifold. Yeah. Dimension is equal to the number of kind of rank of space of Hodge classes.
So this one is the trivial representation, but in one.
Yeah, trivial representation. Yeah, trivial representation. Yeah, it's all this part of the game. Yeah. Now so it's in manifold, and then for any point, you get a spectrum. Yeah, you get this operator, gamma, and it can act on different things. It acts on various spaces. First, it acts on just even on the tangent space to this manifold. Then it acts on all even cohomology of X, and then it acts on all cohomology of X. And the claim that spectrum as a set is the same in all three cases. As a finite subset. Same for all three cases. I mean, like 1, 2, 3. Okay. It's again property of just commutative algebra action on the group, nothing specific. Now, what's the idea? This consider generic point. It's of the submanifold. What do I mean? Points where this number of elements of the subset attains the maximum. This point moves, and some divisors they collide, but there will be some open connected dense domain. Some complement to a divisor. To a closed divisor, where number of these eigenvalues is maximal. Then for each eigenvalue you get still action of this group on this component of the tangent fiber. Each eigenvalue because we get this kind of like, we can surround by little disk. Yeah, okay, we can decompose the whole things in direct sum. For each eigenvalue, we get a representation of this group when extend scalars on the direct summand of the tangent space. And you can look on tangent space in various kind of super manifold, all even part or even just small part, it doesn't really matter. But I consider this on the whole on all cohomology. Yeah, so I get representation, and by this decomposition theorem it will be also subalgebra, and isomorphism class of this representation doesn't change if you move continuously. And the reason is the following: if you get variety, this huge group acts on cohomology through some finite dimensional factors. And then representations are kind of like discrete, have only discrete parameters. The things cannot jump. So the isomorphism classes do not depend on a point, which don't belong to this discriminant. Whatever. Yeah, okay. So that's the basic idea. And sorry, I now have to finish.
So the distinct eigenvalue with respect to the Euler operator?
Yeah, of Euler operator, yeah. Yeah.
So when you say that the group acts locally on something, do you mean that, so it is a Pro group, that when it always acts through a finite
dimensional quotient in the neighborhood of zero, this finite dimensional quotient acts here, yeah.
Okay, so this acts on this complex manifold, it acts through this finite dimensional quotient.
Yeah. Okay, maybe I'll have really, maybe take 5 minutes more to things to finish. Yeah. So what blowup theorem implies? That's a Mumford-Tate spectrum of X tilde. It's the Mumford-Tate spectrum of X plus R minus 1 copies, because it's always a multiplicity of Mumford-Tate spectrum of Z. When you get blowup. And the reason is kind of obvious, because we have this decomposition of my eigenvalues. Algebraic part will be kind of this fixed point will be product of fixed points. And then all things are separated, and you immediately see that you get the same story. Yeah, yeah, so that's maybe I'll really stop. I don't know now. Sorry?
Can you say just?
Oh, maybe I'll say a little bit. Yeah, how these things can be applied to kind of like practical questions for people in birational geometry. Yeah, first I'll just want to say little examples. When X is P2, then you get 3 eigenvalues. They sit in virtues 3 points, and then Mumford-Tate spectrum will be trivial representations repeated three times. But if you get X as a quintic threefold, I still not go to example relations, then the story is the following. If you get gamma equal to gamma 0, consider even part. So if you consider, states any even part. If you consider a linear combination of gammas, then gamma 0 is just a constant. And then a very easy calculation shows that the spectrum of this earlier guy is just one element set. It's minus a constant. Because all these operators, if evil we know gamma 0, all these operators preserves filtrations gamma. This Euler field preserves the filtration by degrees less than something in this case, and gamma 2 gives strictly positive degrees, and gamma 0 gives diagonal operator.
Spec Euler is minus
constant, which is equal to this number gamma 0, because H0 identified with constants.
So the whole spectrum is minus gamma 0.
Just one number,
yes,
depending on this coefficients gamma 0 of my class. And the same true for any variety X and in dimension with canonical class is nef. Could be 0, could be positive. It's just by degree reasons. Yeah, so one can look on this formula and see that the degree reasons is whole thing. Right, and now maybe I'll finish in kind of 5 minutes how one can prove non-rationality of whatever cubic fourfold, which was promised in the very beginning, in the announcement of my lectures. Yeah, consider cubic fourfold in P5. So you get some equation of degree 3 in 6 variables. Suppose it's smooth cubic fourfold. Then Hodge diamond is the following. It will be 1, 1, 21, 1, 1. It will be such numbers. And then it splits into two pieces. It's a restriction of cohomology of P4 restricted to X, powers of ample class, and some other piece in the middle cohomology, some primitive middle cohomology. And assume, so we get something like H4 primitive. And assume primitive contains no Hodge classes, which is true for generic cubic fourfold. It's very easy to understand this variation of Hodge structure, how it looks like. In typical group SO22 for this part, so it will be transcendental part. The claim that this variety is not rational. And the reason is the following. Yeah, there is this part, algebraic part, and given Tal again, when he proves this mirror conjecture, he also calculates something for Fano varieties and kind of calculated action in a certain sense of Euler field on this algebraic part. And it has this eigenvalues will have this multiplicities 1, 1, and 2. It's 5-dimensional space. And when you just took 0 point in your variety in cohomology, you get eigenvalue 0 with multiplicity 2 and 3 eigenvalues and multiplicity 1. And nobody take care about this transcendental part. It was very non-interesting. It also goes to the same part. So you see that for this eigenvalue 0,
it goes to eigenvalue 0? Or?
Yes, to 0, yeah. For eigenvalue 0, you get kind of reducible representation such that dimension of Vg is equal to 2. We have only 2 algebraic classes. Here there's no Hodge classes, two Hodge classes. But still, when consider P minus Q decomposition, this action of GM, you get kind of this P minus Q equal to 2 minus 2 part. It's one-dimensional. And this already gives some kind of statement that such guys cannot appear in this Mumford-Tate spectrum of any point, curve, a surface. Any variety of dimension y of dimension less than 2. For points and curves, it's clear because you don't have h to 0. And for surfaces, it's a little bit tricky argument. One should use birational classification of surfaces. Classification of surfaces. And then one can see that surfaces will have abelian surface, K3, and general type. And for general type, they have some AD singularities. One can resolve them. K3, abelian, and general type. But general type with ADE singularities. I can say the surfaces is H2 0 non-zero. And then you can resolve the singularity and then result singularity. This canonical class will be not positive, will be non-negative. And here canonical class is 0. So you see that from these guys, you automatically gets only one point on the spectrum always. And here, the dimension of cohomology with G will be at least 3, because you get classes in H0, H2, and H4. You get at least 3 Hodge classes for any surface. Yeah, so such guys cannot appear from surfaces. Even if it's decomposed fuzz, it still cannot come from the surfaces. And this proves rationality, because when you make blow up and blow down, if you go to projective space, in projective space you get just points. You get a very stupid Mumford-Tate spectrum. You change by things of coming from varieties of codimension 2. And this piece cannot cancel with something in codimension 2. Okay, that's roughly a scheme
Is it a new result or what?
It's a new result. Yeah, people, in kind of birational geometry, for them, it's kind of they struggled with this result for 60 years. We weren't able to get it, and this is kind of really first application to really interesting questions on Greek geometry, I have to say. Not how many, 20,000, whatever. Blah, blah, blah. Okay. Okay, thank you. I think.